Okay, so in this video, we're gonna plot the Mandelbrot set using SDL. Pretty much, it's really simple. If you don't know how to get the Mandelbrot set, pretty much here, I'll just show you in Python pretty quickly. So if I open Python, what I can do is I can say I have a complex number called z, and this complex number is going to be 0, 0. So the real portion of this is going to be 0. The imaginary portion is going to be 0. Hit enter. And then I have a position I want to test. So my position is going to be C. I'm going to assign that to a complex number. This complex number is going to be something like 0.5 and 0.5. So the real portion is 0.5. The imaginary portion is 0.5. Click enter. And pretty much the way that the Mandelbrot set is computed is you do z is equal to z squared. In Python, 2 asterisks means power, so z to the power of 2 plus c. Click enter. I look at z, it's 0.5 and 0.5. I run this operation again. I check z. I see that it's a 0.5 and 1. I run this a whole bunch of times. Let's check z. Okay, so as you can see, we went outside of acceptable range. So for example, in this example, we have this value is negative 31,000 something, and the imaginary portion is 1,200 something. So pretty much the whole thing that we're doing is we're going to iterate through this, and we're going to check is z, when we do z is equal to z squared plus c, if we do this, let's say 1,000 times or 100 times, does this stay within some certain bounds? So if it stays in certain bounds, then it's in the set. If it doesn't stay in the certain bounds, it's not in the set. And that's pretty much how the Mandelbrot set works. So let's actually get back to the code. Okay, so this is going to be an SDL, so obviously you're going to include SDL. Since we're dealing with numbers, we're also going to need the numeric library. Also, you're going to need to include complex. So let's just do our standard boilerplate for SDL. Okay, so what's going on? Well, pretty much what I did is I initialized SDL, then I created window pointer and a render pointer. Then I passed those pointers into this create window and render function, which basically just creates a window and render for us. Then what I did is I set the render set scale. This is only because I have a high resolution display, so for things to appear on YouTube better, I just like to multiply it by 2 just so that you guys can see it better. But yeah, again, this is just the boilerplate. This has nothing to do with the Mandelbrot set. Okay, so what are we doing? Well, pretty much what we're doing is we're looping from 0 to 1, and we're incrementing I by 0.01 every time we loop. In J, we're doing the same thing, so we're looping from 0 to 1, and we're incrementing by 0.01. So what's going to happen is we're going to iterate through I and J, and we're going to check if I and J, so in this example, what I'm going to do is I'm going to use I and J as the X and Y coordinates. So I'm going to say I is the X coordinate and J is the Y coordinate. Actually, I think it'd be easier if I just rename I to X and Y. Let me just do that right now. Okay, so what we're doing, if it's easier to understand, so what we're going to do is we're going to loop over every X, and then we're going to loop over every Y, and I'm going to check, is point XY in the Mandelbrot set? And to do that, we need to define a special function, which is basically this function here. So z is equal to z squared plus c. So we need to define this function, and we're going to do it up here. So this function is going to return an int, and I'm going to call this is in set Maybe I should put underscores here. So this function is going to be called isInSet, and it's going to take a complex number. So I'm going to accept complex. So again, in this function, c is going to be a complex number that I'm going to pass into this isInSet function. Then what we're going to do is going to loop over to simulate the iterations. So we're going to say for int I is equal to 0, I is less than 25, actually maybe 100. So depending on how accurate you want to be, you can either go from 0 to 25 or 0 to a million or 0 to 10 billion. So this really depends on you. It really depends on how much processing power you want to waste. So for me, I don't want to waste a lot of processing power, so I'm just going to say I is equal to 0, I is less than 25, and then I'm going to do I plus plus. Okay, so now what we're going to do is going to compute z is equal to z squared plus c. And that reminds me, I have to create a z. So I'm going to do a new complex z, and I guess this is just going to be 0 and 0. So I'm making a new complex number, and this is going to be called z, and it's going to begin at 0 and 0 every single time. So for every single point we pass in to c, so for every single point we pass into isInSet, z is going to begin at 0. So it's going to begin at 0 for the real portion and 0 for the imaginary portion. Okay, so finally what we're going to do is we're going to compute z is equal to z squared plus c. So what we're going to do is we're going to say z is equal to z to the power of 2 plus c. Okay. And then what we're going to do is we're going to check, are we outside, or did we... and then we're going to check if this point is still in the set. So is this still close enough for us to consider it to be in the set? And for that, we're going to use the norm function. So we can say std norm. I'm going to pass in z. So what does this actually do? Let me look it up. Okay, so what does this do? So how are we using this? We're passing in z. Okay, so that means that we're calling this one. Yeah. Okay, so it's returning a squared magnitude of the complex number z. So in this case, what I'm going to say is I'm going to say if this norm, so if the squared magnitude, so if the squared magnitude of the complex number z is greater than 16 or maybe 32, it really depends up to you. So you can put whatever number you want in here. So I'm just going to say if it's greater than 10, then what I'm going to do is I'm going to return I. So this is... So the reason we're returning I is because, so later on, if we want to color this Mandelbrot set, we're going to check how many iterations did it take us to realize that this number, so this position C, is not in the set. And if it's not in the set, we're going to use this number, this I, to color it some color depending on how we want to color it. Anyways, let's actually continue. So basically, if this squared magnitude of z is greater than 10, we're going to return I. Otherwise, we're going to return 0. So if we get 0, that means that this is inside the set. So we are inside the set. We're fine. Okay, so this is pretty much the only thing you need. This is literally the only function. So this function is like 99% of the Mandelbrot set. It's pretty much all you need. Okay, let's actually go down. Okay, so what we're going to do is going to do a linear interpolation. And we're going to do a linear interpolation between... Let me just look up the reference. Okay, so we're going to compute the linear interpolation between, let's say, -2 and 2. And we're going to pass into this x. So the way that this is going to work is it's going to give us the point that we want to check for the x-axis. So my x-axis goes from -2 to +2. So we're doing a linear interpolation between -2 and 2. And the reason we have x go from 0 to 1 is because the linear interpolation accepts values from 0 to 1. So we don't want to go above 1. So basically what I'm going to do is I'm going to just say double point x is equal to this value, and then for point y, I'm going to do okay. So now that we have that, what we're going to do is we're going to create a complex number. Or I'm just going to pass it in. I'm just going to pass it in. I'm going to create the complex number as I pass it in. So I'm going to say is in set, and then do std complex. So what we're doing here is we're asking how many iterations did it take to realize whether or not this is in the set. So if it's in the set, let me just go back to this function. So if this is inside the set, so if this is inside the Mandelbrot set, we're going to get 0. So any point which is inside the Mandelbrot set, and again, when I say point, I mean C. So if C is inside the Mandelbrot set, we're going to get 0. Otherwise, we're going to get I. And I is going to be a number from 0 to 25. So depending on how many iterations it took to realize that this number, or this complex number C, is not inside the Mandelbrot set, is what I is going to be. So I is going to return to us either a 0, or should I say, this function is going to return to us either 0, or it's going to return to us I. And if it returns to us I, it's going to be something between 0 and 25. I hope that makes sense. Okay, so what I'm going to do is I'm going to say if iters is equal to 0, then what I'm going to do is I'm going to do SDL draw. Make sure you pick SDL render point f, because f accepts floating point numbers. If you do just point, it's not gonna look as well. Okay, so what I'm gonna do is I'm gonna pass in a render. Actually, let me check what the. Okay, so yeah, you have to pass in a render first, followed by float x and float y. So what I'm gonna do here is I'm gonna pass in point x and point y, and actually also multiply this by 1000. Okay, and before we do that, we also have to set a color. So what I'm going to do is I'm going to set this all to 0 because we want black. So anything that's inside a Mandelbrot set is black. Anything that is outside of it is going to be a different color. Okay, and else, what we're going to do here is we're just going to copy this, paste. And I guess what I can do is I can just do something like this. I can say 255 minus iters. Okay, that should be fine, I think. Okay, let's see if this works. Okay, let's see if this works. Okay, so what I'm going to do is I'm going to compile this. I'm going to do g++ dash std is equal to c++ 20. Make sure you set your standard to 20 because otherwise you're gonna have a bad time. Next up, we have to link SDL. And finally, pass in the Mandel. Okay, let's see. Oof. Okay, I know I shouldn't do this, but I'm just gonna disable warnings for this. Okay, that's fine. Okay, so what do we have? We have a bunch of pixels like this. This is not what I want. Okay. This is not what I want whatsoever. Let's actually let's not multiply this. Okay. What's going on here? Okay, that looks better. So what we have here is, oh, okay, I see what's going on. Let me close this. Okay, I see. Okay, so instead of using point X and point Y, I think I'm just going to use X and Y. Okay, and there you go. That's the Mandelbrot set right there. Now, the colors aren't coming through that well, so I think I'm going to... let's just change some stuff around. So instead of doing minus iterers, let's do times. Let's multiply this and let's take the modulo of 255. And maybe let's multiply it by a different number. So let's multiply it by 2, 3, 4. Save this. Yeah, that looks better. So it has a little blue glow around it a little bit. Let's increase a little bit. So maybe like this. Okay, that looks a lot better. But the problem I still see here is that it's kind of crude. It doesn't have a lot of it's not that complex. So let's increase the iterations. So let's take the iterations from 0 to 25 to maybe from 0 to 200, 250. So we're going to iterate from 0 to 250 and we're going to check with that. Let's compile this again. That looks better, I guess. Maybe not that uniform. Maybe I should just make this all the same. Now, keep in mind, the higher you set your iterations, the longer it's going to take to actually render this out. So to get a higher detail picture, you probably would want to reduce this a little bit, so maybe do something like this. But I warn you, this is going to take a long time. So let's say if I do 0.01, save this, compile it. As you can see, this just looks like nothing. It's a bunch of pixels. But if I reduce it like this, I'm going to reduce the iterations too because they're taking a long time. So if I compile this and I run this, Okay, so to wrap it up, basically what you need, this is what you need. You basically need this is and set function, so you can call it whatever you want. Basically what I'm doing here is I'm passing in a complex number, so I'm saying std complex double c, so I'm passing in the c. This c is being, I'm just going to show you how it's being passed in. So what I'm doing is I'm running for double x from 0 to 1, and I'm incrementing x by 0.01. And for y from 0 to 1, I'm incrementing y by 0.01. Then what I'm doing is I'm doing a linear interpolation. So basically what this does is it gives you every number from negative 2 to 2, depending on this x. And the thing is, you can't have a linear interpolation between maybe, let's say, negative like 5 and positive 5. You can't do that. It has to be within 0 to 1. So basically what I'm doing is I'm running this linear interpolation from negative 2 to 2. I'm getting point x and point y. So this point x and this point y are going to be the points that we're going to test inside of this is set function. So what I'm doing is I'm creating a new complex number, and I'm creating this number from point x and point y that we just created up here. Then when this function finishes, it's going to return to us iters. So if iters is greater than 0, that means that whatever we got back is not in the set. So what I'm doing is I'm testing is iters equal to 0, so are we in the set? If we're in the set, what I'm doing is I'm setting the draw color to be black, and I'm drawing basically 0, 0, 0, 255 is the alpha, and then I'm drawing that point. So I'm drawing x, y times 1000. The reason I'm multiplying by 1000 is because I want to scale x and y by 1000, and x and y are only going to be numbers between 0 and 1. So if I multiply by 1000, it's going to be a number between 0 and 1000, which is our resolution. So our resolution is 2000, but because I'm doing SDL set scale too, the real resolution here is 1000. So imagine it's just 1000 times 2, 1000 times 2. This is pretty much the same thing, but basically our real resolution is 1000, but because I'm scaling it by 2, the way that it appears on the screen is 2000 by 2000. I hope that makes sense. Basically, if our point is in the set, our iters variable is going to be 0. Therefore, I'm going to paint it black and draw that point. Otherwise, if it's not, I'm going to do some coloring. So I'm not sure if this is a good way to color the Mandelbrot set. You should play around on your own with this. But pretty much what you can do is you can say, okay, so here's some funky coloring we're going to do based on how many iterations it took to determine whether or not this is in the set or not. And finally, what I'm doing is I'm just rendering out x and y times 1000, x and y times 1000, same thing. Then we're presenting this to the window, and we're waiting 10 seconds, and then we're just going to exit. So yeah, that's pretty much the Mandelbrot set. I hope you enjoyed it. If you want to see it again, I'll run it, just so you can see. There you go, that's the set. I hope you enjoyed this video, and I'll see you later.